Friends, welcome to the tutorial series on network analysis made simple. During the previous tutorials titled Introduction to Laplace Transforms and another titled Special Signal Waveforms Step Function, we learned the basics of Laplace transforms and the detailed study of step functions. During this tutorial, we shall discuss regarding ramp function. You know that a ramp in general is a sloping surface joining two different levels. But in electrical network, a ramp is a signal whose magnitude may gradually increase or decrease in time. We shall see this in detail. So friends, in this tutorial, we shall learn the various ramp signals and their representation. We also find the Laplace transforms of unit ramp, delayed ramp and so on. Hope the discussion will be lively and interesting. Friends, here are a few ramp signals. Observe the function shown in figure 1. It is a ramp of A units which occurs at t is equal to 0. Let me substantiate this statement. Observe that the function has a slope of A units, that is A divided by 1. This is said to be the strength of the function. Note that for unit time, the magnitude of the function increases by A units. So, it is called as a positive ramp. Further, the magnitude of the function is 0 for t less than 0 and it starts increasing at t is equal to 0. Note that. So, the function is said to occur at t is equal to 0. It is represented by f of t is equal to a into r of t. Its mathematical model is f of t is equal to 0 for t less than 0 and is equal to at for t greater than or equal to 0. Hope it is clear to you. Next, consider another ramp shown in figure 2. Observe the function. It is a shifted ramp of A units which occurs at t is equal to a seconds as shown. It is also called as a delayed ramp. Its slope is equal to A units, so it is a ramp of strength A units. Its magnitude is 0 for t less than a seconds and it starts increasing at t is equal to a seconds. So it can be said to occur at t is equal to a seconds. Then it can be represented as f of t is equal to a into r of t minus a as shown in figure. Its mathematical model is f of t is equal to 0 for t less than a seconds and is equal to at for t greater than a seconds. It is also a positive ramp. Next, consider another ramp shown in figure 3. Observe the function. Its slope is equal to 1 unit as its magnitude increases by 1 unit in unit time. So, it is called as a positive ramp of 1 unit. It also can be called as a unit ramp which occurs at t is equal to 0 as it starts increasing at t is equal to 0. So, it is represented as f of t is equal to r of t. Hope you understand it. Its mathematical model is f of t is equal to 0 for t less than 0 and is equal to t for t greater than or equal to 0. Next, consider another ramp shown in figure 4. Observe the function. It has a slope of 1 unit. Its magnitude is 0 for time t less than a seconds. It starts increasing its magnitude at t is equal to a seconds. So, this function is said to be a delayed unit ramp which occurs at t is equal to a seconds. It also is a positive ramp. So, it is represented as f of t is equal to r of t minus a. Its mathematical model is f of t is equal to 0 for t less than a seconds and is equal to t for t greater than or equal to a seconds. So, to represent and identify any given function, you will have to find its slope, and you will have to identify the time at which the magnitude start increasing or decreasing. We shall discuss the representation of a negative ramp as we proceed further. Friends, now let us find the Laplace transform of a ramp of A units which occurs at t is equal to 0. This function is shown in figure 1. We know its mathematical model f of t is equal to 0 for t less than 0 and is equal to at for t greater than or equal to 0. So, by definition, we know that L of t is equal to integration 0 to infinity f of t into e to the power of minus st dt. By substituting the value of f of t, we get L of f of t is equal to integration 0 to infinity at into e to the power of minus st dt, or L of f of t is equal to a into integration 0 to infinity t into e to the power of minus st dt. To find the integration of this equation, we have to use integration by parts. We know the rule of integration by parts, which states that u into dv by dt is equal to u into v minus integration v into du by dt. That you know from our equation. Let u is equal to t, so du by dt is equal to 1. And let dv by dt is equal to e to the power of minus st, and we get v is equal to integration 0 to infinity e to the power of minus st dt, and that we get v is equal to e to the power of minus st by minus s. So, by substituting the respective values in the equation of L of f of t, we get L of f of t is equal to a into bracket t into integration 0 to infinity e to the power of minus st dt minus integration 0 to infinity e to the power of minus st divided by minus s into 1 into dt. By solving it, we get L of f of t is equal to a into 1 divided by s into 1 divided by s, and hence L of f of t is equal to a divided by s square. So, L of a into r of t is equal to a divided by s square. Friends, once we find the Laplace transform of a ramp of a units which occurs at t is equal to 0, the Laplace transform of other waveforms can be found very easily. For example, to find the Laplace transform of a delayed ramp of a units which occurs at t is equal to a seconds, we can use the time displacement theorem, which states that L of f of t minus a is equal to e to the power of minus as into f of s. So, the delayed ramp is shown in figure 2, and its Laplace transform L of a into r of t minus a is equal to a into e to the power of minus as divided by s square. Similarly, to find the Laplace transform of a unit ramp which occurs at t is equal to 0, the same derivation which we did earlier can be used, and by substituting a is equal to 1, we get L of r of t is equal to 1 divided by s square, and the Laplace transform of a delayed unit ramp will be L of r of t minus a is equal to e to the power of minus as by s square. Friends, till now we discussed only positive ramp functions. Now we shall learn about negative ramp. Consider a negative ramp function shown in figure 1. It is a negative ramp of a units which occur at t is equal to 0. Observe that its slope is minus a divided by 1, which is minus a units. Its magnitude starts decreasing at t is equal to 0. So, its mathematical model is f of t is equal to 0 for t less than 0 and is equal to minus at for t greater than 0. This function is represented as f of t is equal to minus a into r of t. So, its Laplace transform L of minus a into r of t is equal to minus a divided by s square. Observe the ramp shown in figure 2. It is a negative delayed ramp of a units which occurs at t is equal to a seconds as it has a slope of minus a units. Its mathematical model is f of t is equal to 0 for t less than a seconds and is equal to minus a t for t greater than or equal to a seconds. Therefore, its Laplace transform L of minus a r of t minus a is equal to minus a into e to the power of minus a s by s square. Observe another ramp function shown in figure 3. It is also a negative unit ramp which occurs at t is equal to 0. So, it is represented as f of t is equal to minus r of t. Mathematical model is f of t is equal to 0 for t less than 0 and is equal to minus t for t greater than or equal to 0. So, its Laplace transform is L of minus r of t is equal to minus 1 divided by s square. Friends, consider another negative ramp shown in figure 4. It is a delayed negative unit ramp which occurs at t is equal to a seconds. Note, it has a slope of minus 1 unit. So, it is represented as f of t is equal to minus r of t minus a. Its mathematical model is f of t is equal to 0 for t less than a seconds and is equal to minus t for t greater than or equal to a seconds. Hence, its Laplace transform is L of minus r of t minus a is equal to minus e to the power of minus as by s square. Friends, it is very simple, isn't it? Next, we shall take up some examples and learn to handle the ramp signals. Consider the function shown in figure. We are required to find the Laplace transform of a given triangular pulse. If you observe the figure carefully, you find that there is a unit ramp which occurs at t is equal to 0. Its slope is 1 by 1. Let it be f1 of t and f1 of t is equal to r of t. But the given function takes turn at t is equal to 1 second. See figure 1. So, at t is equal to 1 second, we have to add a negative ramp such that the resulting function proceeds along the given waveform. Let us see what happens if we add a unit negative ramp at t is equal to 1 second as shown in figure 2. A negative ramp at t is equal to 1 second is minus r of t minus 1 as shown in figure 2. The result of adding these two ramps results in a straight line parallel to the x-axis as shown in figure 3. So, to turn the horizontal line, we have to add another negative ramp of 1 unit at t is equal to 1 second. So, to turn from the original direction of f1 of t, we have to add the negative ramp of twice the slope, that is minus 2r of t minus 1 at t is equal to 1 second. If we do this, the resulting function travels down crossing at t is equal to 2 seconds. Note that. But the given function is 0 after t is equal to 2 seconds. So, we have to add a positive unit ramp at t is equal to 2 seconds. This positive ramp is r of t minus 2. So, finally, we get the equation for f of t as f of t is equal to r of t minus 2r of t minus 1 plus r of t minus 2, and by taking the Laplace transform, we get L of f of t is equal to 1 divided by s square minus 2 e to the power of minus s by s square plus e to the power of minus 2s divided by s square. Friends, let us solve another problem to find the Laplace transform of a given waveform shown in figure. Observe the given waveform. Hope you find a positive step of 5 units at t is equal to 1 second. So, let f1 be 5 u of t minus 1. Next, we have to turn the direction at t is equal to 1 second. Observe that there is a negative ramp of minus 5 divided by 2 units at t is equal to 1 second, and let f2 is equal to minus 5 divided by 2 r of t minus 1. By adding it to f1, we get f of t is equal to 5 into u of t minus 1 minus 5 divided by 2 into r of t minus 1. If we do so, the waveform proceeds further down with a slope of minus 5 by 2 units crossing at t is equal to 3 seconds. Note that. So, to turn the direction and to make it to proceed along the x-axis, we have to add a positive ramp of the same slope of 5 by 2 units at t is equal to 3 seconds. So, f3 of t is equal to 5 by 2 r of t minus 3. So, by adding all the three functions, we get f of t is equal to 5 u of t minus 1 minus 5 divided by 2 r of t minus 1 plus 5 divided by 2 r of t minus 3. By taking the Laplace transform, so we get f of s is equal to 5 into e to the power of minus s by s minus 5 by 2 into e to the power of minus s by s square plus 5 by 2 e to the power of minus 3s by s square. Hope you got the technique. Friends, now let us solve another example to find the Laplace transform of the given sawtooth waveform. Hope you are able to identify a positive ramp of slope a divided by t at t is equal to 0. Let it be f1 of t, but the given waveform turns vertical at time t is equal to t seconds. So, at time t is equal to t seconds, if we add a negative ramp of the same slope a divided by t, the function takes the horizontal direction as shown in figure 2. Let it be f2 of t is equal to minus a divided by t into r of t minus t. Now, to bring the function vertically down at time t is equal to t seconds, we have to add a negative step of a units. Let the function be f3 of t is equal to minus a into u of t minus t as shown in figure 3. Therefore, the resultant function f of t is equal to f1 of t plus f2 of t plus f3 of t. By substituting the values, we get f of t is equal to a divided by t into r of t minus a divided by t into r of t minus t minus a into u of t minus t. By taking the Laplace transform, so we get f of s is equal to a divided by t into 1 by s square minus a divided by t into e to the power of minus ts by s square minus a into e to the power of minus ts by s. Friends, next we shall solve another interesting problem to sketch the waveforms of the two functions. It is given that f of t is equal to 2t. And first let us consider the function number 1 f of t minus 2 into u of t. It is given that f of t is equal to 2t. You know that this is a positive ramp of 2 units which occurs at t is equal to 0 as shown in figure 1. Now, if you look at the given expression, the first term is f of t minus 2. You know that this is a delayed ramp of f of t delayed by 2 seconds. This function is shown in figure 2. This function is to be multiplied by u of t. You know that the function u of t is equal to 0 for t less than 0 and will be equal to 1 for t greater than or equal to 0. So, u of t also is shown in figure 2. If you observe the two functions between the time 0 to 2 seconds, f of t minus 2 is 0 there. So, the resultant will be 0 for time between t is equal to 0 to 2 seconds. But after t is equal to 2 seconds, u of t is 1. So, after t is equal to 2 seconds, the resultant will follow f of t is equal to 2t. The final waveform is shown in figure 3. Hope you understood it. Now we shall plot the waveform given by f of t into u of t minus 2. This is tricky and interesting, friends. The first function is f of t is equal to 2t and is plotted as shown in figure 1. Note that the slope of the function is 2 units. This function is to be multiplied by u of t minus 2. You know u of t minus 2 is a delayed unit step function which occurs at t is equal to 2 seconds as shown. It is interesting to note that the resultant function now is 0 between 0 to 2 seconds because u of t minus 2 is 0 till 2 seconds. Therefore, after t is equal to 2 seconds, the function will follow f of t is equal to 2t. The resultant final waveform is shown in figure 2. It is interesting to note that the integration of a step function results in a ramp function. Consider a step function of a units which occurs at t is equal to 0. You know that it can be represented as f of t is equal to a into u of t. We also know that its mathematical model is f of t is equal to 0 for t less than 0 and is equal to a for t greater than or equal to 0. Let this function be true for time between 0 to t seconds. Then by integrating this step function for time t is equal to 0 to t seconds, we get integration 0 to t f of t dt. By substituting the values and solving, we get integration 0 to t f of t dt is equal to at. The result we obtained at is the straight line having slope equal to a units between 0 to t seconds. But you know that the ramp function of a units also is represented as f of t is equal to a into t, and this ramp is represented as f of t is equal to a into r of t. Thus, we can say that the integration of a step results in ramp function. Friends, in this tutorial, we defined a ramp function, found the Laplace transform of unit ramp, delayed ramp. To emphasize the concepts we have learned, we solved a few numerical examples. Also, we learned to plot the given function and find their Laplace transform. During the next tutorial, we shall learn modified ramp and impulse function. Friends, if this tutorial has kindled some of your thoughts, please forward your feedback and suggestions to my email. Thank you for watching this video.